Section 2.9, inverse functions. So we're going to begin talking about inverse functions, but the first thing we need to look at is one-to-one and what one-to-one means. One-to-one means that each y value corresponds to only one x value. Okay, graphically, if we're looking at it, that means that the graph has to pass the horizontal line test. Now, one-to-one is kind of the opposite of a function. Okay, if we know something is a function already, that means that every x value corresponds with exactly one y value. One-to-one is going in the opposite direction. So every y value goes to a specific x value. Okay, and again, just a refresher, a function must pass the vertical line test, where in order for it to be one-to-one, it must pass the horizontal line test. Now, if you look down here at this f to the negative 1x, that's what it looks like. This is the notation for an inverse function. Okay, so this f raised to the negative 1 of x is just the notation for inverse. Now, algebraically, we can figure out if two functions are inverses by doing the composition. If I do the composition of two functions, so if I do f of g and I get x, and then I in turn do g of f and I also get x, then I know that these two functions, f and g, are going to be inverses of each other. Now, in previous sections we've talked about domain many times. We are going to go in detail again about the domain of a function and a domain of the inverse. Well, an inverse, again, is a flip-flop of the x and y values. So the domain of your original function, domain of your original, is going to be equivalent to the range of the inverse. And the domain of the inverse is going to be the same as the range of the original. All right. One other thing we're going to be doing is we're going to be solving or finding the inverse of a given function, and there are two steps. Your first step is to switch your x and y values. Okay, I'm sorry, x and y, not x and y values, but literally flip-flop the x and the y variable. Then, if you solve for y, you will come up with the inverse function. Example 1. Assume the function is one-to-one with domain negative infinity to infinity. If f of negative 2 is equal to 7, then find f inverse of 7. So let's look at this in terms of a function machine. Okay, here's my machine. When I put negative 2 in, it's saying that it's going to spit out 7. So negative 2 goes into my function f of x, and a 7 comes out. Well, remember, an inverse is going in the opposite direction. Okay, the inverse machine goes in the opposite direction. So if this is my inverse machine, it's saying if I put in 7, what's going to come out? Well, remember, these go hand in hand. So when I put in 7 into the inverse machine, I'm going to get out negative 2. So if they tell us f of negative 2 is equal to 7, then I know that the inverse of 7 is equal to negative 2. Okay, because this x value corresponds with this y value, and if they give us the y value, they are really asking what's the corresponding x value. So the answer is simply negative 2. Example 2. For f of x equals x cubed plus 5, find each of the following. So they give us this function, okay? F of x equals x cubed plus 5. The first thing we're trying to find is f of 2. And we know that simply means to take this 2 and plug it into the function wherever we see an x. So f of 2 is equal to 2 to the third power plus 5. 2 to the third is 8. 8 plus 5 is equal to 13. Okay, so f of 2 is equal to 13. Now I just want to show you that means we have the ordered pair 2, 13. Okay, so the answer to this part is 13, but I just want you to know that that means when we plug 2 in, we get 13 out, so the corresponding ordered pair is 2, 13. Now, part B asks us to find the inverse. Okay, so remember, the inverse is going in the opposite direction, so what they've really given us here is the y value. They're telling us the y value is 13. So algebraically, I can look at the function f of x equals x to the third plus 5. And I can plug 13 in for the y, okay? We know that f of x is the same as y. So I can change it to 13 equals x cubed plus 5. I'm going to go ahead and subtract 5 from both sides. That gives me x cubed equals 8. All right, I'm going to write that up here. 8 equals x cubed. Now to get rid of a cube, we're going to cube root both sides. Okay, we're going to cube root. The cube root of 8 is 2, so we get x is equal to 2. So my answer is 2. Now, you didn't have to go through all that work. If you recall in part A, when we plug an x value in of 2, we get a y value out of 13. And we know an inverse goes in the opposite direction. So they said, hey, we have a y value of 13. What x value does that correspond to? Well, I could have just looked at this ordered pair from part A and say, oh, I know 13, a y value of 13 corresponds with an x value of 2. So you could have come up with 2 without doing any work. Now, knowing that, let's do part C. F of f inverse of 13. So f of f inverse means we're going to put it in the one function and then put it through the next function. Okay, so we're going to do f and f inverse. We know that f goes in one direction, the inverse goes in the opposite direction. So basically they're undoing each other. So when you see this f of f inverse, you can think about this just kind of undoing each other. So the answer is simply just 13. Now, you can do it algebraically, but the easiest way to just think about this is that when you put a value in and then you go backwards back to that value, you get what you started with, which is 13. For example 3, we're going to find f of g of x and then g of f of x to determine if the functions are inverses of each other. Excuse me, if you refer back to the notes that we took on the first slide, it shows us, let me go back real quick, that two functions, so I'm right here, two functions are inverses of each other if and only if, when you do the composition of f of g, you get x, and when you do the composition of g of f, you also get x. So back to our example, let's do both of those. So we're going to do f of g of x first, and again, our goal is to see if we get x. So f of g of x, which means we're going to do f of 2 minus x divided by 3. So I'm going to take 2 minus x divided by 3 and I'm going to plug it into the f function right there for the x. So that's going to leave me with 2 minus 3, and again I'm going to take that x out and put this new stuff in, times 2 minus x divided by 3. Now I'm going to simplify that. That gives me 2. Now notice, this 3 in the numerator and this 3 in the denominator are going to cancel out. So 2 minus, don't forget your parentheses, 2 minus x. I'm going to go ahead and distribute that negative. That's going to give me 2 minus 2, and then minus this negative x is going to give me plus x. So I'm left with x. Okay, that's exactly what I wanted. When I do the composition of f of g and I get x, I'm on the right track. So now I have to go over here and verify what g of f of x equals. So g of f of x. So I'm going to do g of 2 minus 3x. That means I'm going to take 2 minus 3x and plug it in for this x in the g function. So that gives me 2 minus, and I put it in parentheses, 2 minus 3x divided by 3. Go ahead and distribute the negative in the numerator. So 2 minus 2, and this minus a negative becomes plus 3x, all divided by 3. And then 2 minus 2 is 0, so I'm left with 3x divided by 3. And I see that those 3's will cancel out, so I'm left with x. So when I did the composition of f of g, I got x. When I did the composition of g of f, I also got x. And it says that if you get x when you do both of those compositions, then you know that they are inverses. Okay, and that's what the question was asking. Determine if the functions are inverses of each other. And we see that they are inverses. Example 4. We have several parts. A says determine whether the function is one-to-one. B, if the function is one-to-one, find its inverse. Part C, graph the function and its inverse on the same coordinate axes. And then part D, state the domain and intercepts of the function and its inverse. Okay, so the first thing we need to do is determine if this function is one-to-one. Okay, when we look at this, we know g of x equals 2x plus 5. We know that that is the equation of a line. So I'm going to write it as y equals 2x plus 5. Okay, now I know part C says to graph, but I'm going to go ahead and graph that now. Okay, just so I can visually see if this function is going to be one-to-one. So when I'm graphing y equals 2x plus 5, my y-intercept is a 5, so I'm going to start up here with a dot at 5, okay? And the slope is 2, so I'm going to go up 2 over 1. And then I'm going to connect those dots. And I know it's not going to be perfect, but I see that it's a line with a slope of 2. Does that pass the horizontal line test? Well, it does. So this is, in fact, a one-to-one function. Yes, it's one-to-one, okay? Because visually, when I graph it, I see that it passes the horizontal line test. Now, going back, part B says if the function is one-to-one, then we're going to find its inverse, okay? So, going back to the steps from, again, the first page of our notes, it says the steps for finding the inverse function down here at the bottom. We're going to switch x and y, and then we're going to solve for y. All right, so let's go back to our function, our example. We have y equals 2x plus 5. Remember, g of x means y. So I'm going to switch x and y, so that's going to give me x equals 2y plus 5. Again, you just literally flip-flop where the x and the y are located. That's step 1. Step 2 says to solve for y. So to solve for y, I'm going to subtract 5 from both sides. That's going to leave me with 2y on the right-hand side and x minus 5 on the left-hand side. My last step to get y by itself is to divide by 2. And I'm going to do this for each piece, okay, instead of doing it as a whole. That's going to give me my function x divided by 2 minus 5 halves is equal to y. So what is the inverse equal to? G inverse of x is equal to, I'm going to write it as 1/2 x minus 5 halves. Okay, G inverse of x is equal to 1/2 x minus 5 halves. That is another equation of a line. This time, the y-intercept is negative 5 halves, and the slope is 1/2. So let's go down and graph that. Okay, so again, the y-intercept is negative 5 halves, so that's negative 2.5, so somewhere right around here. All right, and the slope is 1/2, so from that point, I'm going to go up 1 over 2. I'm going to go up 1 over 2. And then I'm going to connect those. So my line's not going to be perfect, but you get the idea. Graph doesn't look very nice. I went ahead and made another graph that's a little bit neater to look at. So My original function was g of x equals 2x plus 5, okay, and I have that right here. Then my inverse that I just found was g inverse of x is equal to 1/2 x minus 5/2. So you see I graphed both of those, and it's a little bit neater on here. Now one thing I want you to notice is that these two lines, they're inverses of each other. They have this little property where I'm going to try to draw a little dotted line. If you look at the line y equals x, which goes right through the center of this graph, okay, you can see that they are mirror images of each other. So they have symmetry across the line y equals x. So go ahead and jot that down somewhere. And a function in its inverse have symmetry across the line y equals x. Okay, and again, this line right here is y equals x going right down the center of the graph. Okay, so every function in its inverse will have that kind of symmetry. Now let's move on. Let's talk about domain of our original function and our inverse function, and the intercepts of the original function and the inverse function. Domain, let's start there. Domain of g of x. Okay, domain of g of x, so we have to look at our original function. Let me slide this over. Look at our original function, 2x plus 5. And we have to say, are there any restrictions? Well, there's no fractions, and there's no radicals, so we have no restrictions, meaning the domain is negative infinity to infinity. Now, domain of the inverse. Okay, domain of the inverse. Well, I have, again, this inverse function here. I have to look at restrictions. Yes, there are fractions, but there's no x in the denominator. So I don't have to worry about that rule. There's no value that's going to make the denominator equal to 0. Then there's no radicals. So again, I have no exclusions. So the domain of the inverse is also negative infinity to infinity. All right? And then the last part, I'm going to go ahead and look at what are the intercepts of g of x. What are the intercepts of g of x? Now, you can do this algebraically, or you could look at the graph. Well, I know that the original function has a y-intercept of 5, okay? I know that that's my b, okay? So that is the point 0.05. That's my y-intercept. Now I also need the x-intercept. So let's look at it algebraically, okay? Y equals 2x plus 5. I'm going to go ahead and write it down here. Y equals 2x plus 5. If you remember, to find an x-intercept, you make y 0. So let's put 0 in for y. So 0 is equal to 2x plus 5. When I solve that, I'm going to subtract 5 from both sides. So negative 5 is equal to 2x. Then I'm going to divide both sides by 2. And that gives me x equals negative 5/2. So what I just found was the x-intercept. So the x-intercept of my original function is negative 5/2, 0. And I can look on the graph. I see that my original function is this line right here, g of x. All right, it's this one right here. I see the y-intercept is 5, and I see the x-intercept is about negative 2.5. Now my graph's not perfect, but I see that it should cross at negative 2.5. Now, let's look at the intercepts of the inverse. Well, again, I'm given the y-intercept. The y-intercept is negative 5/2. Whoop. Let me erase. Not the x-intercept, the y-intercept. The y-intercept is negative 5/2, so that gives me 0, negative 5/2, because that is my b in my equation in the form y equals mx plus b. And then I have to go ahead and I could solve for the x-intercept, but I don't need to. Notice the x-intercept of your original function is now the y-intercept of your inverse. The same thing's going to happen. This y-intercept of your original is going to be the x-intercept of your inverse. They're always going to be flip-flops, so you don't have to solve for it again. So we have an x-intercept and a y-intercept for the original function, and then we flip-flop those and we have the x-intercept and y-intercept of the inverse function. Example 5. Find the inverse of the function f of x equals the cube root of x plus 6. Again, we're referring back to the two steps. Let me write them up here. First step is to switch x and y. And step 2 is to solve for y. Okay, so I'm going to replace this f of x with y. So it's going to be y equals the cube root of x plus 6. All right, I'm going to switch my x and y. So that's going to give me x equals the cube root of y plus 6. So that's step 1. Step 2 is to go ahead and solve for y. So I need to get this y by itself, which means I'm going to have to get rid of this plus 6, and I'm going to have to get rid of this cube root. Well, to get rid of cube root, so I'm going to rewrite what I have, cube root of y plus 6. To get rid of a cube root, you cube both sides. All right, cube root and cube cancel out. So that leaves me with x cubed is equal to y plus 6. Again, I'm trying to get y by itself, so I'm going to subtract 6 from both sides. So that gives me x cubed minus 6 equals y. I'm going to rewrite it with my y on the left-hand side. So y equals x cubed minus 6. So formally, the way I would write this is the inverse, f inverse of x, is equal to x cubed minus 6. That is the inverse of the cube root of x plus 6. Example 6. Find the inverse, then state the domain and range of the function and its inverse. So let's start by going through the steps of finding the inverse. Again, I'm going to take f of x and I'm going to make it a y. So I'm going to have y equals 3 divided by x minus 2. First step is to switch x and y. So that's going to leave me with x equals 3 divided by y minus 2. Now, that's step 1. Step 2 is to now solve for y. Well, the first step is to get rid of these fractions, okay? By getting rid of the fraction, you're also going to bring y out of the denominator. So to do that, you're going to multiply both sides by y minus 2. Multiply both sides by y minus 2. So on the left-hand side, I'm going to rewrite it as x times y minus 2 is equal to, notice on the right-hand side, the y minus 2's cancel out. So equals 3. Again, my goal is to solve for y, so I'm not actually going to distribute this x, I'm actually going to get rid of it. So to do that, I'm going to divide both sides by x. So these x's are going to cancel out. So that gives me y minus 2 is equal to 3 divided by x. My last step would be to add 2 to get the y by itself. So y equals 3 over x plus 2. So I'm going to write this up here as the inverse of x is equal to 3 over x plus 2. Now that I have my function and its inverse side by side, so I just found the inverse, the next part of this question asks us to state the domain and range of the function itself and its inverse. So I need to find the domain of f of x, and I need to find the range of f of x. And f of x is my original function. I also need to find the domain of the inverse, f inverse of x, and the range of f inverse of x. Let's start with domain. Okay, when I look at my original function right here, my original function is f of x equals 3 divided by x minus 2. When I look at that, I say, do I have any restrictions? Remember, I have to look at denominators and radicals. Well, I don't have a radical, so the only thing I have to deal with is this x minus 2 in the denominator. I know that I take that denominator, x minus 2, and I set that not equal to 0. When I solve that, that tells me x cannot equal 2. So the domain of f of x, if I write that in interval notation, is going to be negative infinity to 2, union 2 to infinity. So that is my domain of f of x. All right. Now, if you refer back to the original page, the first thing we did at the beginning of the notes, I'm going to flip back to it. It says that the domain of your original is equal to the range of your inverse. And the domain of your inverse is equal to the range of the original. So going back, I can now take this domain of my original and write it down here as the range of the inverse. So the range of the inverse is also negative infinity to 2, union 2 to infinity. So there's no work required. The range of your inverse is exactly the same as the domain of your original. Now, for the inverse, let's go ahead and find the domain of the inverse. So here's my inverse function, 3 over x plus 2. My only restriction is in the denominator, so I know that x cannot equal 0. No solving required. So to write that in interval notation, I'm going to write negative infinity to 0, union 0 to infinity. That is the domain of my inverse function. And again, I know that the domain of my inverse is the same as the range of my original, so I can copy that over here. Negative infinity, 0, union 0, infinity. Okay, so again, it's like a crisscross. The domain of your original is equal to the range of the inverse, and the domain of the inverse is equal to the range of your original. Example 7. Find the inverse, then state the domain and range of the function and its inverse. So let's start by finding the inverse. So I'm going to rewrite this as y equals x plus 1 divided by x minus 3. Now I have two x's this time, but that's okay. I'm still going to follow the steps. Step 1 says switch x and y. So it's going to become x equals y plus 1 divided by y minus 3. Okay, again, step 1 is to flip-flop x and y. Step 2 is to go ahead and solve for y. So I have a fraction. Let's go ahead and get rid of that. So I'm going to multiply both sides by y minus 3. All right, so that leaves me with x times y minus 3 on the left-hand side and y plus 1 on the right-hand side. Now I have y's on both sides, so somehow I've got to get them on the same side. So the first thing I'm going to do is distribute this x on the left-hand side. That's going to give me xy minus 3x is equal to y plus 1. All right. Then, again, I want my y's on the same side. So I'm going to go ahead and I'm going to do minus y. I'm going to move this y to the other side. So I'm going to go ahead and write that up here. That leaves me with xy minus 3x minus y is equal to 1. Again, my ultimate goal is to get y by itself. So anything that doesn't have a y needs to go to the right-hand side. I'm going to add 3x to both sides. So now I have xy minus y on the left-hand side is equal to 1 plus 3x. All right, and we looked at this in a previous section on the last exam. When I have these two separate y's, I need to combine it somehow and get it to down to just one y. And to do that, you're going to factor out a y. When you factor out a y, you're left with x minus 1. And on the right-hand side, we still have 1 plus 3x. My last step, again, I want to get y by itself, so I'm going to divide both sides by x minus 1. So that gives me y equals 1 plus 3x over x minus 1. So I know that this is now my inverse. I had made a little room. So now I have my original function is f of x equals x plus 1 divided by x minus 3. My inverse is inverse of x is equal to 1 plus 3x divided by x minus 1. So again, I need to find the domain of my original and the range of my original. I also need to find the domain of my inverse and the range of my inverse. All right, so we know that the ranges will just fall into place. So let's find the domain of each of these functions. My original function has a denominator that we have to worry about. Remember, the restriction is to take the denominator, which is x minus 3, and set it not equal to 0. So that tells us that x cannot equal 3. So I'm going to go ahead down here for the domain of f of x and write that in interval notation. That interval notation is going to be negative infinity to 3, union 3 to infinity. Now remember, these two go hand in hand. So I can go ahead and copy that as the range of the inverse. So negative infinity to 3, union 3 to infinity again. So now my next step is to find the domain of the inverse. Again, I have a denominator to deal with, so I take that denominator, which is x minus 1, and I set it not equal to 0. That tells me that x cannot equal 1. Writing that in interval notation down here for the domain of the inverse, that's going to be negative infinity to 1, union 1 to infinity. And again, I know that these two go hand in hand, so the range of my original is also negative infinity to 1, union 1 to infinity.